Welcome to my presentation. My name is Bagus and I am from Japan Advanced Institute of Science and Technology. In this talk, I would like to present my work entitled Multitask Learning and Multistage Fusion for Dimensional Audiovisual Emotion Recognition. This paper was written by me and Masato Akagi of JAIST. Let's start with the outline of my presentation. First, I will show you the motivation of my works, then what's the problems and what's my proposed solution. The third is methods, including two, multitask learning and multistage feature fusion. And then I will show you experiment results. And finally, I will summarize my presentation with some conclusions. So let's move to the motivation. Currently, most research in emotion recognition have been conducted on categorical view, that is recognizing whether an utterance or facial expression conveying happy, sad, anger, or other emotion categories. However, we think that it is necessary to go to beyond categorical view, that is dimensional view. Why? Because dimensional view will enable us for deeper analysis. For example, in categorical view, we only know the category of emotion like happy, sad, anger, but we don't know how strong the happy, how weak the sad. So in this research, the dimensional emotion like valence, arousal, and liking are our targets from audio and visual modalities. So what's the problem? There are two problems here. First, since there are three attributes, valence, arousal, and liking, which is here, the first problem is how to predict those three attributes simultaneously. The second problem is since there are multiple results from different feature sets from two modalities, acoustic and visual, the second problem is how to combine those results from different feature sets from both modalities, audio and visual. And here is my proposed solution. For the first problem, we propose to use multitask learning to predict three attributes of emotion dimension, valence, arousal, and liking simultaneously. For the second problem, to combine different results from different feature sets, we propose to use multistage SVM to combine those results from both modalities. So let's move to the data and feature sets we use in this research. For the dataset, we use part of CIWA dataset used in AFEC 2019, Audiovisual Emotion Challenge last year. This dataset originally contains of three languages, German, Hungarian, and Chinese. German and Hungarian are used for training and development, while Chinese is used for the testing. However, because the testing dataset is not available, we only use the dataset for training and development, that is German and Hungarian. And for feature sets, we use two modalities, audio and visual. We use 7 acoustic feature sets from audio and 4 visual feature sets listed here. Gmaps, function of Gmaps, and deep spectrum from audio, MFCC, and FAU for visual. Let's move to the methods. First, we use CCC loss-based cost function. CCC is acronym of concordance correlation coefficient here. So it can be formulated as 2 multiplied by Pearson correlation of x and y, where x is the true value and y is the prediction, multiplied by standard deviation of x and y, divided by variance of x and y, and added by mean of x, subtracted by mean of y square. So this is the metric we use to measure the performance of our system. So for loss function, we can use the opposite of CCC, that is CCC loss, which is defined by 1 minus CCC, because the maximum value or mapping score of CCC is 1. So we can minimize the CCC loss for training the data set. And because there are three attributes or three dimensional emotions, arousal, valence, and liking, we sum up the loss function from three attributes: CCCLA for arousal, CCCLV for valence, and CCCLL for liking. And we give each dimension a weighting factor, for example, alpha for arousal, beta for valence, and gamma for liking. And we sum up those three CCC loss to get the total loss. So this is the heart of the MTL or MTL approach. So this is the architecture of our dimensional emotion recognition using DNN, our deep neural network. Here, the input is acoustic feature and our visual feature. And we use three LSTM networks stacked together. And after that, we split the last output of LSTM into one unit dense layer to represent or to predict arousal, valence, and liking here. And here the calculation of CCCL on the previous slide. So the MTL is calculated here, and we obtain the result or the prediction of the arousal, valence, and liking in continuous degree here. So for example, if the input is audio feature, we will obtain an prediction from audio feature here, and if the input is audio and visual feature, bimodal feature, we will obtain also the similar size of the prediction here. So this is the implementation or the application of the previous MTL concept in the architecture. That's for the first problem, the solution for the first problem. And for the second problem, we propose to use SVR, support vector regression. This is the part of SVM, support vector machine, to combine different results. So from the previous slide, we obtain result from unimodal, for example, from audio acoustic or acoustic feature, and then using another feature set, for example, bimodal feature, using audio and visual feature, we obtain the another result. So we use SVR here to combine both results. So the input is the result from a feature set and another feature set, and the output is also the prediction of valence, arousal, and liking. So we can see here we will have another result, say result 3 from the previous input, and we can perform this one stage. We call it as one stage multimodal emotion recognition for several steps. In this research, we perform until 5 stage or 5 steps to obtain the final result. So this SVR fusion approach is proposed to tackle the second problem for combining different results, because we have 7 audio visual feature and 4 visual feature. So each feature set will give different results. So this is the how to combine different results. So to obtain the final results, the following steps are performed. For example, first we use unimodal acoustic feature to obtain a result, and then a combination of acoustic and visual feature, here bimodal feature set. The acoustic and visual feature are concatenated and fed to the same previous architecture to obtain the input, and we have different output or different results. And to combine unimodal and bimodal results, we use SVR fusion. We call it as multimodal emotion recognition or one stage SVR. And if we perform this multimodal SVR several times, we got the result for multistage SVR fusion. So to obtain the final result, the best result here, we perform the following steps. And this is the result. First, we present the result for unimodal MTL approach compared to the STL or single task learning. As baseline, we optimized each emotion dimension. For example, in the first method, STL1, we optimized arousal and we got the highest CCC score. CCC score is an arousal. valence lighting slow because we optimize arousal. On the second method, we optimize valence, and we see here that we got the best CCC score on valence. However, in the third method, when we optimize liking, the best method is not in liking but in valence. Here, liking is the most difficult, and although we already optimize liking, still the result, the highest score for each emotion dimension is not in liking but in valence. And as comparison, we also evaluated another MTL from this reference from the interspeech. They propose to use MSE, mean square error, with two parameters for MTL, and we applied their MTL approach to our data set here, used here, and we got improvement over STL. And finally, when we applied our MTL approach here, the last one, with CCC based loss function and three parameters, we got the highest result for all emotion dimension, arousal, valence, and liking. So here our MTL approach to predict arousal, valence, and liking works well and obtained higher performance compared to STL and previous MTL approach. The next is results from multistage SVR fusion by combining different results. So as baseline, we use FAU feature set, which is used in the baseline paper here, and we, they show a fair result for arousal and valence. And this unimodal is from the previous MTL using acoustic feature only. We already improved here, particularly on valence, and we use bimodal early fusion by concatenating acoustic and visual feature, and we improved, I think, particularly on liking dimension, and we use one stage SVR, or we call it as multimodal light fusion, and we improved again in all dimension and thing. And finally, when we perform this one stage SVR 5 times or 5 stage, we call it as multistage fusion. We got here the highest performance on CC score for arousal, valence, and liking. Particularly on liking, the score is doubled from the MTL unimodal. So we can see here that our approach by combining different results using SVR obtain the highest performance. So how about the use of different stage in a multi-stage SVR? So we analyze here using one stage to 5 stage. There are slight improvement on arousal and valence. However, on liking, the performance is doubled from 0.2 using one stage SVR and to 0.4 using 5 stage SVR. We only limit until 5 stage due to computation limitation. The result maybe will be higher if we use more stage, but also the computation time and more than these 5 times. So we can conclude here that first, our proposed SCCC-based multitask learning with 3 parameters works to predict degree of valence, arousal, and liking. A remarkable gain was obtained over single-task learning from the highest single-task learning 0.297 to 0.431 using our MTL approach. And furthermore, we improved the score from MTL to a multi-state SVR, from unimodal to a multimodal by combining different results. We improved from 0.431 from the previous one to 0.593 using our multi-stage SVR. I think that's all for me. And if you have any question, please ask. Thank you very much.